Think about the last time you walked up to an ATM. You slide your card into the slot, punch in a few numbers, and wait. In that moment, the machine feels like a personal, intelligent bank vault, one that knows exactly who you are and how much you're worth. We tend to assume this heavy metal box is tracking our financial lives in real time, reading our account balances and deciding whether or not to grant us access. In reality, the machine is completely blind. It holds no local data on your identity, your history, or your bank account. To the hardware inside the machine, an account with $1 million is indistinguishable from an account with $0. It has no way to tell the difference. This creates a unique architectural challenge. If the machine is essentially clueless about your money, it has to verify your identity and calculate your funds across a massive distance, with zero margin for error, in a matter of seconds. Because it lacks internal data, the ATM operates as an isolated node, relying entirely on an external communication link to function. The process begins when the card chip makes contact with the machine's internal reader. This provides the only local data point the machine will handle before the network takes over. Immediately, the machine establishes an encrypted digital tunnel, a secure, direct connection linking the street-level hardware to your bank's central server. Your PIN and identity data are packaged into encrypted blocks and sent down this pathway at nearly the speed of light. Once data reaches its destination, the ATM stops thinking. The remote server handles the decision-making logic, running several checks simultaneously, confirming the PIN, verifying the account is active, checking the balance, and assessing the transaction for fraud indicators. If any of these checks fail to return a positive result, the server terminates the transaction immediately. If every check passes, the server fires back a single approved command through the tunnel to the waiting machine. The ATM acts as a relay, waiting for authorization from a remote commander before it can engage its physical hardware. When that digital signal arrives, the internal hardware of the ATM reacts instantly. The machine transitions from data processing to heavy mechanical action. Inside, the machine stores cash in individual cassettes. The system calculates the specific combination of bills required to fulfill your request and starts the sorting process. High-speed rubber rollers begin spinning, generating enough friction to strip individual paper bills from the stacks one at a time. But paper currency is rarely in perfect condition. Because the rollers move so quickly, bills often stick together, tear, or fold. To prevent errors, bills pass a laser array measuring thickness and geometry. Sensors look for overlapping bills, folded corners, or tears that cause jams. If detected, a trapdoor flips down, diverting the damaged currency into a secure internal reject bin. The exterior shutter only opens once the sensors confirm that every note in the stack meets the required physical standards. This mechanical filtering process ensures the user receives a clean, accurate chunk of bills, regardless of the condition of the currency inside the cassettes. The encrypted handshake, the remote server checks, the mechanical sorting, and the laser verification all take place in less than 5 seconds. The ATM functions as a high-speed relay, executing commands issued by a remote server through a series of mechanical gates and sensors. A simple cash withdrawal represents a precise alignment of global data networks and mechanical hardware. But even with these safeguards, systems can experience rare failures. If the machine ever lost its precision and dispensed more cash than you requested, what would you do? Let us know in the comments.